Okay, for this reaction, we're going to look at a single replacement reaction, also called a oxidation reduction or redox reaction. It's a pretty simple reaction. Aluminum foil, I've just cut it into a square. You can note the appearance of the aluminum foil. It's silver, shiny material. Just going to kind of fold it a little bit so it'll fit into the test tube. I'll put it down into the test tube. They're going to add this blue aqueous solution of copper chloride. It's actually copper 2 chloride. So we're going to add this. Let's see what happens. So remember, silver, shiny, and the blue solution, add to it. We're just going to cover the aluminum. And this reaction, as opposed to the other two that we've done, not quite as exciting as the other two. You do get a little bit of gas formation there, which is a side reaction we're not going to focus on. But you can see pretty clearly that the aluminum foil is definitely changing. So what you can see here is that it's no longer silver and shiny. It's actually kind of looking brown, reddish color. And as we let this sit long enough, what you would actually see is that the blue solution will actually eventually become colorless. And so you can see I've knocked off some of the substance that's forming on the aluminum foil into the bottom here. I don't know if you can see, but it's like a reddish brown color. So we'll let this sit. We might come back to it after the other explanations so that you can see the different color changes. You can definitely see now a pretty good, nice red color. And there's not a lot of evidence now of the aluminum foil in its original form that I can see. Kind of finger vortex it around here, get it stir up. You can definitely see that the blue solution is fading. We get lots of bubbles. And so now you can really see the fading of the blue solution. And the aluminum foil is not there in its original form anymore. Okay, so that's what it looks like to your eye, so you're macroscopic. Also, the test tube gets really, really warm here. So it's an exothermic or heat-releasing reaction. Okay, so for this reaction of the particulate view, I'm going to draw the particulate view myself, just to kind of show you don't have to have pre-made cards. So let's take a look at how I would do this. So I've got the copper chloride solution. Just like with the hydrochloric acid solution and the sodium hydrogen carbonate solution, this is ionic substance, so it's going to dissociate into its ions. So what I'm going to do is I'm going to just draw a little key up here. So I'm going to have my copper plus 2. I'm going to have that just be a open circle. My chloride ion, I'm going to have that be a closed circle. I'm going to draw it a little bigger, because negative ions are usually bigger, or are bigger than positive ions. And so that's my copper chloride solution, what it's going to look like. And then my aluminum metal. So my aluminum ion, I'm going to just draw as a stripe, like that. Okay, notice not charged, because it's the element, the aluminum foil. And then, of course, since we have a solution with the copper chloride, we're going to have our water molecules there, and I'm just going to draw them kind of like that, so you can tell that's water. Okay, so in this first circle, I'm going to draw my copper chloride solution. So I've got, here's my formula. So let's talk a little bit about kind of how stuff breaks up. If you look at this substance, when it dissociates, you're going to get 1 copper, but you're going to get 2 chloride ions. Okay, and you can see that from the formula. 1 copper, 2 chlorine, so we have to balance it out here. And so for every 1 open circle that I draw, how many negative circles am I have to draw? I have to draw 2, right? 1, 2. Okay, and we'll draw one more just for style here. Okay, see that? And then, you know, water is going to be in this because it is an aqueous solution. This is the positive ion, and so the water is going to orient around like this because water is polar. And here's the negative ion. Water is going to orient around like this. Okay. And so on. I'm not going to draw the rest of the waters there, but you kind of get the picture of what's going on. And then for the aluminum metal, I'm going to draw another circle. A little bit smaller because I don't want to draw so many aluminum atoms. And so since it's a solid, how would I draw those? I draw them tightly packed, right? Just going to kind of quickly draw a few here. And then we'll put our stripes in because they're the aluminum. So get the picture there. Okay. So then if you look in our reaction, you saw that nice red solid that was forming. Well, that red solid is actually copper metal. Okay, and you saw that the blue solution kind of went away, and we got a colorless solution, and that's because these copper ions are changing into a solid. These aluminum atoms are changing into aqueous because you have a redox reaction. And so when you mix these two together, your picture would look a little different. And I'm going to kind of show it as it was in the test tube. So if you notice, your solid particles will kind of sink into the bottom. And so now this copper ion here is now a solid. So we'll show that down here. And I'm not sticking to my mass conservation here for my model, which is okay. All right, so there's my copper solid sunk to the bottom, right? The chloride ions don't change. So I'm going to stick to my conservation of mass with that one. That's one of the shortcomings of models sometimes, is that they don't always show that. The water, excuse me, is still present. And I'm just going to draw enough to show you around this ion. Okay, so there's the water still present. And then these aluminum atoms become charged. Aluminum actually gets oxidized in this reaction, and copper is reduced. So I'm going to show the aluminum up here because now it's ionized. Okay, and so this symbol now represents this. Okay, because the aluminum changed. This symbol now represents this because the copper changed. Notice that the chloride remained unchanged, the water remained unchanged. And so this is pretty good particulate level view of the reaction. Definitely not as good as our pictures that we have, but a little bit that you can see. You can do this yourself as well. So we've definitely had it change. Okay, so now we're going to look at this symbolic, and we're going to go through the net ionic equation again, like we did with the last one. So we had our copper chloride solution, so we write aqueous, plus aluminum solid, okay. What forms is copper solid, that was the red solid that you saw at the bottom of the test tube, and aluminum chloride solution, okay. And so copper, when it's in the ion form, is a nice blue color. Aluminum ion is no color, it's colorless. And so this is our overall equation. What you can see, though, is that we need to balance this out. So what we're going to do is balance it right now. And so if you look, you have one copper here, so that's good. You have 2 chlorines and 3 chlorines, so those are not balanced. So we're going to use our least common multiple between 2 and 3, which is 6. And so we're going to have to put a 3 here. Okay, and so that's going to give us 6 chlorines. And so how can we make 6 chlorines over here? We're going to multiply by 2, like that. Okay, but when we do that, when we add those coefficients, we're actually changing the copper and aluminum numbers as well. So we got to go back and fix that. So here I now have 3 coppers, but 3 times 2, so 6 chlorines. So I got to put a 3 in front of my copper. So now it's balanced. And then if you look here, we have 2 aluminums, but only 1, so we can put 2. And so now it's balanced. So 3 copper chlorides react with 2 aluminum to form 3 coppers and 2 aluminum chlorides, like that. Okay, so next we're going to go through our complete ionic again. So remember from the last example, when you see aqueous like this, these are going to dissociate to their ions, and I try to draw that with my particulate level view. And so what we're going to have here, and we're going to keep up with our numbers, so we've got 3 copper ions, and then how many chloride ions do we have? 3 times 2, 6 chloride ions. See how that's working? Aluminum solid, it's not an ion, so we just keep it the same. So plus 2Al, like that. Copper solid, it's not an ion, so we just leave it the same. See? And then here, it's aqueous, so we got to dissociate it out. So we see we have 2 aluminum, that's going to be a plus 3. And we have 2 times 3, which is 6 Cl minuses. Okay? And so if you remember from the last example that we did, once we got to our complete ionic, we started crossing stuff out that wasn't changing, like I referenced in the particulate level. And so if you notice, copper ion to copper solid, that's a change. Okay, blue solution, red solid, definite change there. 6Cl minus, 6Cl minus. Same on both sides, no change there. So we're going to cross it out. And then 2 aluminum solid, nice silvery aluminum foil like you're used to seeing. And then aluminum ion, a colorless solution, so a change there has occurred. And so from this, we can now write our net ionic, which is going to be 3 copper plus 2 aluminum. And I'm going to go ahead and put my phases back in now. I just didn't have room to write them before. 3 copper solids plus 2 aluminum ions, aqueous. Okay, and so this is our net ionic equation now that we've got. And if you look here, you can see this is called a single replacement reaction, and it's also a redox reaction. Up here, let's talk about single replacement real quick. What you see happening here is that the aluminum is switching out with the copper, and so there's been a single replacement. That's where the name comes from. And then down here, you can see more clearly the redox reaction that's occurring, or the oxidation reduction reaction. And so here you have copper at a plus 2 oxidation state. Here, copper solid has an oxidation state of 0. And so since we went from a 2 to a 0, our oxidation state went down. That means that the copper was reduced. Okay, electrons were added. And if you look here at the aluminum, we see an oxidation state here of 0 because it's the element or solid. Here you see a plus 3. And so our oxidation number went up. It increased from 0 to positive 3. So this is an oxidation. We've lost electrons.